So we're going to talk about first passage percolation on the lattice. So what is this model? So this model was introduced by Hammersley and Welch in 1965. So this is a model for fluid flow through inhomogeneous media. So let me draw a picture first. So I have the lattice, and on the edges of the lattice, I put some random weights. So these are random numbers. So this is, let's say, 0. So the idea is that I start with, say, some fluid at the origin, and then these random numbers denote how much time it takes for the fluid to pass through this particular edge. So tau1, which corresponds to the weight of this edge, it will signify that after time tau1, water that was initially there has percolated through here. Okay, so it tells you that after time tau1, this vertex now has also become wet. Okay, so how to make this formal? So we have the tau e. So EZD will denote the nearest neighbor edges in the lattice ZD. It will be a sequence of IID random variables. And then for any path gamma, so a path is a finite sequence of edges such that the endpoint of one edge is the starting point of the next. We define the passage time of gamma, which we denote by L gamma. So I have a path gamma. Let's say this is my path gamma. Then the passage time is simply tau1 plus tau7 plus tau8 plus tau9. Okay. So I just simply sum the taus along the path, and I call this L of gamma, the passage time of gamma. Now, what I want to measure is that how much time does it take for the fluid to percolate from a vertex to another. So suppose my vertex U becomes wet at time t. I want to know how much longer it will take for the vertex V to become wet. So at start, say I start from the vertex U, which is wet at time 0. I want to know at which time will the vertex V become wet. So this is measured by the following first passage time. So first passage time from U to V. So this is simply, I should also say that tau's are non-negative, because otherwise it does not make much physical sense. So I take all finite paths gamma connecting U to V, and I look at the passage time of the path, and I take infimum over all such paths. So that gives me the first passage time between U to V. And you can see this is exactly what I said. So if you take U to be 0, then for the fluid to percolate to V, it has to go through some path, and this T UV is the smallest time it takes through all possible paths. So this is the first time this vertex V becomes wet. Okay, right. So one other thing to observe is that because we have assumed the edge weights, the passage times on the individual edges are non-negative, we can simply restrict ourselves to non-self-intersecting paths here. So if if any path has loop, you can simply cut out the loop, and the weight will only decrease. Okay, so a few observations. So T is random so this is easy to see because simply I'm taking minimum over paths. So it satisfies all the properties of a pseudometric. The reason it's not a metric is because we are allowing tau is to be equal to 0. So it's possible that there are two distinct vertices. The first passage time between whom is 0. So it's not a metric a priori, but it's a pseudometric. So what are the objects of interest? The object of interest, so one important object is the metric ball. Let me say B tilde at T. So this is simply the metric ball of size T centered at the origin. So the reason I have put a tilde here because I want to reserve the notion B for something else. I'll simply denote and one other thing I should also mention is that for me, D will always be bigger than or equal to 2. Okay, so the reason I do this is because I want, so eventually we want to talk about limits of these balls. So we want these sets to be subsets of RD with non-empty interiors for start. So you should think of this definition of B as simply extending the definition of the first passage time to all pairs of points in RD. So this minus half power D is kind of arbitrary. You can also do it like 0, 1 power D. That's another convention. But we want to kind of fill out all of RD. That's what we're doing by adding this minus half power D. Okay, so what are the statistic of interest? So one is like large scale behavior of T. Large scale behavior of B. So large scale behavior of T as the distance between U and V, the Euclidean distance between U and V becomes large. And then large scale behavior of B as T becomes large. So we want to understand their first order behavior, fluctuations around the first order behavior, and so on. And then a second object of interest is the large scale behavior of the optimizing paths. So that are the geodesics. So under mild conditions, as you'll probably see later, that these infimum in the definition of TUV is attained. So you have some gamma, possibly more than one, such that TUV is the length of gamma for path gamma connecting U and V. And it's interesting to understand the geometry, the large scale geometry of these geodesics. So these are some of the most fundamental questions in this model. Okay, so let's first state some basic results, and we'll prove some of them. So let's see. So instead of trying to understand all of B at first, let us first look at a fixed direction. So we want to understand how this T grows when we are moving in a fixed direction. So the simplest direction is E1. So let us look at the sequence. So I look at the origin, and then I look at the point at distance n in the direction of the positive direction of the first unit vector. So E1 is the first unit vector, the vector 1, 0, 0, 0. Right. So let's make some assumptions. So tau I is, I'll assume that their IID following some distribution f. As I have already said, f will be non-negative. So f0 minus f is the distribution function of the edge weights. So f0 minus is 0. And we'll also define something. So we'll define y to be the minimum of 2D many independent copies of f. Okay, so this is going to be important. So here's the first theorem. One thing also I should mention is that everything I'm doing in this lecture, it's contained in the following two references. So the first one is this book by Michael Jack and Antonio Offinger. And then there's also this survey by Keston. So this is in this Barkhauser series, Progress in Probability, volume 54. Yeah. So everything I'm doing in this lecture, you can find it in these two sources. So look at chapter 2 of this 50 years book, or the first section of the Keston notes. Okay, so here is the first theorem. Okay, so it says that if you assume that expectation of y, so remember y is this minimum of 2D copies of f. So if y has finite expectation, then at least along direction E1, you have convergence, and the convergence is almost surely as well as in L1. Yes. Okay, yes. So right. So this one. Okay, yeah. So this one, if you, I mean, I guess the book is available on the MS bookstore or something like that. But so a free version is available on arXiv. But as Michael and Jack said, maybe it's a bit outdated. But it's perfectly fine for this material. And this one you can access if you have access to Springer Link. So, for example, if you are connecting through ICTS Wi-Fi, you should be able to access this one as well. Right. Okay. Good. So let's see. So let's give a quick proof of this one. So the basic observation is that the sequence is subadditive in the sense that so this is simply triangle inequality for metrics. So if I go from 0 to m plus n times E1, I would do at least as good as going first to n times E1 and then from n times E1 to m plus n times E1. And because my underlying environment is translation invariant, this has the same law as, so this is equality in distribution. So then, you know, this seems very similar, like very familiar. It's similar to this Fekete lemma if you had like a sequence of deterministic real numbers. Okay, so how to make this into a proof? What we need to use is the Kingman subadditive ergodic theorem. So I'll just state it without proof. This is a very important tool used in the study of FPP, LPP, and many other similar processes. Okay. So I have a triangular array of random variables. Satisfying a bunch of conditions. So one is the subadditivity condition. The second one is the stationarity condition. So for any fixed m, if you look at this, so if you look at x m plus k, the sequence as k varies from 1 to 3 up to infinity is the same as the distribution of the sequence if you look at the same thing for m plus 1. The next hypothesis, which is the ergodicity hypothesis, is 1. Yes. Yes. No. You're sorry. Yeah. So this is x is a two-indexed family of random variables. So x m plus 1 comma m plus 1 plus k. Correct. Thank you. Okay. So this is the third one, and then there is a fourth one, which I should probably write on this side. So it's simply a moment condition. So it says that x01 has finite mean and x0n in expectation does not decay to minus infinity in a superlinear speed. So these are some technical assumptions, and under these assumptions, the conclusion is that limit n goes to infinity. Okay, so if you have these four conditions, then x0n, if you scale it by n, will almost surely converge to a constant. So you can see from subadditivity and this hypothesis that this number must be finite. Okay, so how does this apply in our case? So just use subadditive ergodic theorem with xmn So I use the subadditive ergodic theorem with the choice of sequence xmn is the passage time from m times e1 to n times e1. It's very easy to see that it satisfies all the hypotheses except, so the only one that requires some work is this. So all the others are quite basic if you know a little bit of ergodic theory, and you know that product measure is ergodic with respect to translations in ZD. So and all the others are directly verifiable. So the only one that needs a little bit of work and where the assumption on y will be used is this step, that expectation of x01 is finite. This part is obvious because these are all non-negative random variables. Okay, so we will prove that. So it suffices So it suffices. So we will show that as long as expectation of y is finite, then expectation of t01 is finite. One aside is that so t01 is just a single edge connecting them, right? So t01 is at most the passage time of the edge connecting 0 and 1, 0 and e1. So if you assume the first moment of passage times, then it is immediate. But the condition there is actually stronger. So it doesn't need to assume the first moment. It's so it can work even without the first moment of the distribution f. Okay, so yeah.
C greater than 0. I thought I remembered C greater than -infinity.
Well, I'm doing minus cn here, right? Yeah. So yeah, if you don't put that minus, then yeah. So the point is that it cannot grow to minus infinity too fast in a superlinear speed. That's what you need. So I put the minus there. That's why. Well, I should probably say like c less than infinity. That's the more is the correct thing. But anyway, all right. Any other questions at this point? Okay, so let's do this quickly. So observation, they exist 2D edge disjoint joining. This is, it's easy to check because I mean each vertex has 2D edges coming out of it, right? So and you can easily see that you actually can construct using these 2D edges. There will be 2D edge disjoint paths joining 0 and e1, and these are completely deterministic paths. So there is nothing random about it. So what do we want to bound? We want to bound the tail of this random variable, right? So we want to bound something like this. Now, if t01 is bigger than t, that means all of these 2D edge disjoint paths have passage time bigger than t. And there are these edge disjoint paths, these have finite length, right? These are deterministic paths, have finite length. So let's say the length is at most b. So this implies that at least one edge on each of these edge disjoint paths has size bigger than t over b, has a weight bigger than t over b. And then there are b many such paths, b many such edges. So I get probability y bigger than. So no, this is not correct. So this is b to the d. So what I have is b times the probability that product I equal to 1 to 2d, tau I is bigger than t over b. So it's b to the 2d here. So each of these 2d edge disjoint paths must have at least one edge whose weight is bigger than t over b. So the probability of that event is simply b times this. Now these are all edge disjoint, hence independent. So I take a product. Now when I take this product, just by definition, that y is minimum of 2d many copies of tau i's. So this is simply now b is simply a constant. So it says that the tail of t0 e1 decays at most like the tail of y. So as long as y has finite expectation, t0 e1 will also have finite expectation. Expectation of y finite implies expectation of t0 is also finite. So this is the only hypothesis that in the subarrative ergodic theorem that we needed to verify. So when we put it back there, the conclusion of subarrative ergodic theorem is that 1 over n t0 ne1 converges to some constant almost surely and in L1. So this is the constant we call mu e1. Okay. Right. So this is essentially, the most fundamental result, which anything about the first order behavior of first passage percolation, the limit shape and all, essentially hinges on this subarrativity argument. Okay, so it's an exercise to show actually this hypothesis is optimal. I think that will be covered maybe in one of the problems in your tutorial. So that is to show that if you have expectation y is infinite, then this mu e1 cannot be finite. Okay, and also one other observation which we'll use soon is that there is nothing special about the direction e1. So you can essentially do something similar along any integer direction or any rational direction. Okay, so you cannot do it along an irrational direction because you don't have this subarrativity quite, because you don't have essentially necessarily an integer point in the middle. But in any rational direction or any integer direction, at least you can do it easily, the same argument. Okay, so one other exercise if you want to try is to show that if f is non-degenerate, then so what about mu e1, right? So what do we know about mu e1? So one exercise you can try. So exercise. Mu e1. Well, provided that it's a non-degenerate distribution, because if it's a degenerate distribution, if tau is constant almost surely, then of course you will get equality because it will be exactly n times the value if you look at the shortest path, and any other path will be longer. Okay, so the next question. So we have ensured under some condition that mu is finite. I mean so this mu is called the time constant along the direction e1. So we have ensured that it is finite under some assumption on the moments on the tail of the passage time distribution. So the next natural question is that when can we ensure that it is positive? So what is the heuristic here is that, so remember, we have not said that the weights are positive, they're merely non-negative, so they can take value 0. So the idea is that if lots of the edges will take value 0, then it should be possible to find a path from 0 to n times E1 that only uses sublinearly many positive weight edges. So in such cases, the limit constant mu e should be 0. So how and what exactly? So the idea is that if the mass of the atom, the size of atom at 0 of F is large, then mu e should be positive. But if it is small, then it if the size of atom is large at 0 is large, then it should be 0. But if it is small, then it should be non-zero. And how exactly, how large exactly that it should be, that requires a little bit of Bernoulli percolation. So I'll simply, most of you would be familiar with it, but I would simply repeat some of the very basics of Bernoulli percolation. So what is the Bernoulli percolation? So again, I have the same underlying graph. But now my edge variables are IID Bernoulli. So instead of putting non-negative weights, I put 0, 1 weights. Now you should think of this as omega e being equal to 0. I'll call that edge closed, meaning that I'm erasing that edge from my graph. Otherwise, it's open. That means I keep that edge in my graph. So the event that is important here is component. Okay, so I denote by this event 0 connects to infinity is that if I look at the subgraph of open edges, in that subgraph I have an infinite component containing 0. Okay, so it says that the cluster of 0 is infinite. So it's easy to see that. Okay, so let's define something. So let's define theta p to be the probability of this happening, that there being an infinite cluster containing the origin. It's easy to see that theta p is increasing in P. So one defines so as you can see, for p equal to 0, theta p is 0, whereas for p equal to 1, theta p is 1. So we simply define the critical probability. So this is depends on the lattice, of course, PC of ZD, simply to be the supremum of all p such that theta p is 0. So so as you increase p, the probability of the 0 being in an infinite cluster stays 0 for some time, and then at PC, after PC, it becomes positive. What happens at PC is a big open question, at least for dimensions 3 and for dimensions that is not 2 and not too large. But anyway, so there is this PC which is at which this jump happens. So the theorem, how that connects to our previous discussion, is that this is the theorem which I will state but not prove. Says that mu e1 is bigger than 0 if and only if f of 0 is less than PC. So this PC is PC of ZDL, not right. Okay, so this is as our intuition was, if the size of the atom at 0 is small, then mu e1 is indeed bigger than is indeed positive, whereas it's large, if it exceeds PC, then it is equal to 0. Okay, so this is something I'm not going to prove. Maybe this will be dealt with in the tutorial, but this is an important result. We are going to assume it for the next part. So let me also state briefly a couple of useful things about percolation, because it might get it might be used in the later courses. So I'll state two useful inequalities about percolation. So let me first define an increasing event. So I'm still in the setup of percolation. So my probability space is 0, 1 power E of ZD. A is increasing if So what does it mean? So just think of it in the following way, that you have so each omega is a configuration of open and closed edges, right? So an increasing event is such that if you open some more edges, that is, you increase some coordinates, then the event still holds true. So if you look at some particular configuration for which the event holds true, and then you open some more edges, the event still holds true. So that's basically an increasing event. So there are two useful inequalities. So one is called the FKG inequality, which says that if A and B are increasing, then so in other words, it says that increasing events are positively correlated. So if you take so for an example, you take the following. So take any two vertices A and B. Easy to see that there is an open path joining A to B. That event is an increasing event, because if there is a path, it doesn't matter if you open some more edges, there will still be a path, right? So that's an increasing event. So in particular, you can use FKG inequality to conclude that probability that there exists a path from A to B and there exists a path from C to D, that probability is at least the product of the marginal probabilities, because both of them are increasing events. And intuitively, you see why this should be true, right? Because if I condition on there being a path, it should not decrease the conditional probability of there being a path between some other pairs of points. The second one is slightly more complicated. So it's called the BK inequality. So it doesn't really require AB increasing. But you know that's how the classical inequality was proved. So it says, I'll say in a minute what it is. So this here is what is called the disjoint occurrence of A and B. So I have two events A and B, then this A square B, which is called the disjoint occurrence of A and B, is basically the event. So I'm not going to write down the exact definition, but it's the event that you can find disjoint subsets of edges such that A can be verified by looking at the configuration in one, whereas B can be verified by looking at the configuration in the other. So again, going back to the previous example, so if A is the event that A is connected to B and B is the event that C is connected to D, then the disjoint occurrence is that there are disjoint paths connecting A to B and C to D. So there, if you have this disjoint occurrence, BK inequality states that the probability of the disjoint occurrence is upper bounded by the product of the marginal probabilities. So probability that there are disjoint paths joining A to B and C to D is at most the probability that A is connected to B times the probability that C is connected to D. Okay, so these are very useful tools in percolation, and these have some uses in the FPP setting as well. Maybe you will see some of it later, but that I'm not going to speak any more about this. So let's just move on to the next subject, which is the shape theorem. Okay. Yes. So the question. Okay. So this theorem you can think of as a law of large numbers for the passage time along the direction E1. So the shape theorem would be an analog where we are looking at a law of large number for the metric ball itself. So let's just state it first and then we'll see. So various versions of it were already there, so it's by Richardson and also, but the final formulation, which is the optimal one, is due to Cox and Durrett. So what is the statement of the shape theorem? So assume. So first we assume that non-zero condition. So we assume that mu of E1 is positive, and we assume a slightly stronger moment condition. So instead of expectation of y being finite, we assume expectation of y to have a dth moment. So then they exist B deterministic compact complex non-empty interior such that for epsilon bigger than 0. So remember, BT is the metric ball after we have extended the metric to all of our D of radius T centered at the origin. So this tells you that in some sense, BT by T converges almost surely to this limit shape B, where the convergence is in this particular topology. Okay, so this is the statement of the shape theorem. So a couple of observations. One is that if such a B exists, then it must have all the symmetries of the lattice. So in particular, it must be invariant under permutation of coordinates. It must be invariant under reflection. And it must be invariant under rotations that preserve the lattice. Okay, so this is the, as you can see, this is kind of the analog of the limit theorem for the passage time. But now, instead of looking at a fixed direction, we are looking at all directions simultaneously. Right. So in the remainder of this lecture, which is probably about half an hour, maybe not even that, 20 minutes or so. So I will give an outline of the proof of the shape theorem, except that I'm not going to prove for the optimal hypothesis. So I'm going to assume something much stronger than this. So what I'm going to assume, we'll talk about it when we come to that step. So we're going to assume that the passage times themselves have second moment, which is much stronger than this. But the proof is slightly less cumbersome. And one other thing I want to point out is that the hypothesis here is again optimal in the sense that if you have either F0 bigger than or equal to PC, or if you have expectation of y to the d being infinite, then this theorem cannot hold. Okay. Any questions about the statement? Okay, so let's try to see how we can go about proving it. Let us try to look at particularly, projections of this theorem, so to say. So suppose, so this is my BT. Now, how far this BT goes in this direction E1? So remember, this is the vertex, the last vertex that I have reached up to time t. So approximately t0, so let's call this distance x. So t0x should be equal to t approximately, which means that this is mu e1 times x approx. So x should be, so if I take bt over t, then the distance bt over t covers in direction e1 should be approximately equal to, so let's, if I scale it back in time t by t, so this should be approximately 1 over mu e1, right? So the previous theorem tells me that the x for which t0x is approximately equal to t should be such that mu e1 x is equal to t, so x should be t over mu e1. So once I scale, I should get 1 over mu e1. So if I look at so suppose such a B exists, then if I look at its projection into the E1 coordinate, I should see that the boundary of B intersects the E1 axis at distance which should be roughly 1 over mu E1. Now, as I said, similar theorems hold in all rational directions, right? So how do we prove shape theorem? So we take these 1 over mu x's along all rational directions and we stitch them together. That's how we get the boundary of the limit shape B if such a thing exists. So that's precisely what we are going to do. So let's maybe I can I erase this? Right. So let's see, let's define step. So this is the first step. Is that for, so take an x, which is a vector in Rd with all coordinates rational. And let's also assume that x is a multiple 1 over m. So m is some integer, and x is a multiple of 1 over m. So define mu mx is equal to so because x is a multiple of 1 over m, that means m times x is a vector in ZD. So there is no problem in defining this T0 nmx. So we get, so we use the theorem which I just erased about existence of limit constants in rational directions that tells me that this limit exists, almost surely, and in L1. The next observation is that it's easy to see that if x is both a multiple of 1 over m and 1 over m prime, then this definition is independent of the choice of m or m prime. I'm not going to prove that, but it's easy to see. So essentially, what we can do is then we can erase the subscript m. So it's a well-defined. The definition does not depend on the choice of my m. So in particular, because each x in QD will have such an m, we can define this mu x for all points in QD, right? So now step 2 will be to verify certain properties of mu again, which is something I'll not do. These are easy exercises which you can do by yourself. So for all xy in D and R in plus, so all vectors with rational coordinates and all positive rationals R, we get, so this is a homogeneity. So this is mu of Rx is R times mu of x. This is from definitions. Then we have triangle inequality. This is mu of x plus y less than equal to mu x plus mu y. And then positivity, this is something that actually requires a proof. So this is where the hypothesis F0 is less than PC will be used. So as I said, if F0 is less than PC, then mu of E1 is positive. And then it's not a very hard exercise to use that together with triangle inequality as well as the fact that mu must also have the symmetries of ZD to show that mu x is positive for all non-zero x if and only if mu E1 is positive. Okay. So this step, the important ingredient in this step is that theorem. So once you assume that, proving this part is not hard. So this is positivity. So the next one is the uniform continuity. So mu is uniformly continuous in all of QD. This is also a consequence of, so at 0 you prove it by this, and then you use triangle inequality to prove it prove a uniform continuity. Continuity at 0 follows from the homogeneity. Okay, so right. Also, so we define mu 0 equal to 0. So I should also probably say that mu 0 is 0. So what does that mean? So in particular, the uniform continuity means that you can extend mu to all of Rd, and the extended mu, which we'll still call mu, has all these properties. So in particular, mu is a norm. So our candidate for B is simply the unit ball of that norm. Okay, so we're going to prove that the shape theorem holds for that particular choice of B, and these are immediately obvious because the unit ball of a norm in a finite dimensional vector space. Okay, so it must be compact, convex, and has non-empty interior containing 0. So the properties of B are all taken care of. All we need to show that this particular choice of B satisfies this. Right? Okay, great. Any questions so far? Okay, so let's do the main step. So, so we have information about the statistic t, right? So we have to somehow transfer that particular equation, that bt over t contains 1 minus e times b and is contained in 1 plus epsilon times b. We want to translate that into some information about t. So here is the reduction. So let's call it a lemma. For every epsilon bigger than 0 with probability 1, have 0, 8. Well, since all norms are equivalent, it does not matter what norm I choose here. But for convenience, we'll just take the L1 norm. Okay, so it's not the L2 norm, it's the L1 norm. But no, in this inequality, it doesn't matter because all norms are equivalent. So what we're going to show is this. For every epsilon bigger than 0, we have with probability 1 that T0V minus mu V is at most epsilon times norm of V for all V with sufficiently large L1 norm. So that this implies the shape theorem is essentially a matter of definition chasing, which I'm not going to do. So this again you can take as an exercise if you haven't seen that before. But this is what we're going to prove. So let us see. Okay. So the proof of this lemma actually requires what is often referred to as a difference estimate. So let me first state the difference estimate and prove the lemma assuming that, and then depending on the time, we will talk about the difference estimate. It says difference estimate. So this is c bigger than 0, such that sufficiently small with probability 1. So what does it say? Let's take a minute to pass this statement. It says that if I take some u with sufficiently large norm and take a v which is close enough to u, in the sense that the difference between the norm of u minus v is at most epsilon times the norm of u, then the passage time between u and v will also be bounded by some constant c times epsilon times norm of u. So it says that if u is large and u minus v is small compared to norm of u, then the passage time between u and v would be linear in the distance between u and v, in the L1 distance between u and v, and this holds simultaneously for all such v and all such u which is sufficiently large. Okay, so this event holds with probability 1. That's the estimate. So this is the most, this is the core technical part of the proof of the shape theorem. So before going to that, let us just see how using this we can complete the proof of this lemma. So let's define an event. So we're going to define an almost sure event on which this holds. So let's say E is the event that n goes to infinity so so in each direction I know that the limit exists almost surely. Since I can take union bound over countably many things, I can get an almost sure event on which this limit constant is equal to the value of the scaled passage times simultaneously in all such directions. So this is my event E, and then let me also define an event A epsilon. So A epsilon is simply the event in the difference estimate. So let me write it again. So EUV less than C epsilon times norm of U all Z minus V norm of U large. So A epsilon is again probability 1. So difference estimate tells you that A epsilon is a probability 1 event. So what we are going to do is we are going to take an intersection of this A epsilon over some countable sequence going to 0. So let us define, let's say E prime is E intersection I. So we are simply taking this A epsilon, this A epsilon for epsilon equal to 1 over I. Countably many events, each has probability 1. So this set E prime has probability 1. What we're going to show is that on this set E prime, the conclusion of the lemma holds. So on this set E prime, we'll get, probably I should just switch it because I'm taking U here. So maybe just make it U. So we're going to show that on this set E prime, which has probability 1, then you get this this inequality T0 U minus mu U is a little of norm of U. Okay, so this proof is by contradiction. Suppose not. Suppose not. So then there exists a sequence Vn going to infinity. Well, I mean, by this I mean norm of Vn is going to infinity. So in ZD, so Vn will be in ZD such that Vn over norm of Vn. So this is a compactness argument. Convert this to Z in S d minus 1. So this S d minus 1 is not the usual L2 sphere. This is the L1 sphere because our norm is the L1 norm. But I use that notation anyway, such that T0 Vn minus mu Vn is bigger than epsilon times norm of Vn. So this is exactly the contradiction to the statement in the lemma, right? So the statement says that something holds for all large V or all large U. Then if that doesn't hold, then I get a sequence of increasing norm Vn for which this happens. And then I can always get a subsequence for which, so this is the compactness argument, which tells you that if I have such a Vn, then I can always get a subsequence such that Vn over norm of Vn has a limit in SD minus 1. So SD minus 1, remember, it's not necessarily a rational point, but rational points are dense there, right? So we can always approximate this Z by a rational point. So that's what we will do. So let us take, let Y in QD intersection Z. S D minus 1 such that Y minus Z is small. This small, I can take it arbitrarily large depending on epsilon. So I have fixed epsilon to start with. So this Y minus Z, I'll make it as small as I like depending on epsilon. Okay, so now, so let us do some triangle inequality. So let us see. So let's write T0 Vn minus mu of Vn. So this is simply T0 Vn minus T of. So we are going to do a series of successive approximations. So first, I approximate Vn by Z times norm of Vn. Then I approximate Z times norm of Vn by Y times norm of Vn. So this is one term. Okay, I think I should probably write it in another board because this is going to be a long equation. So let me just delete the statement of the shift here. Okay, so as I said, I'm going to approximate Vn successively. So first, an approximation. So Vn is approximated first by Z times norm of Vn. Then and finally the okay. So this is my successive approximation. And now where the fact comes into play is the following: is that I use so this term, so Vn and Z times norm of Vn, their difference is little of norm of Vn. It's bounded by some epsilon times norm of Vn for insufficiently large. So this is less than by the difference estimate. I get that. So this is upper bounded by triangle inequality. This will be upper bounded by the passage time between Vn and Z times Vn, right? So by the difference estimate, this is of the order of epsilon times norm of Vn. Similarly, this, because I have chosen Z minus Y to be sufficiently small, the difference estimate also tells me that this is less than epsilon times norm of Vn. Because Y is a rational direction, and I have assumed that convergence happens in all rational directions. This is also less than some C epsilon times norm of Vn. And the final one is by uniform continuity of mu. So the first two I get of the order of epsilon times norm of Vn by the difference estimate, whereas the final two, one is by hypothesis that convergence happens across all rational directions, and the second one is by uniform continuity of mu. So putting all this together, I get that T0 Vn minus mu Vn is at most upper bounded by some C prime times epsilon times norm of Vn. Well, epsilon is arbitrary, right? So here I could have put some C or C prime also. So that tells me that I have a contradiction, right? So we had assumed that on E prime, the shape theorem does not hold, which means that there is a sequence like that. But then I have used the hypothesis on E prime to get a contradiction to this particular statement, which means on E prime, this must hold. Okay. Any questions? Right. So if you have not seen this before, it takes a minute of thinking, but there is nothing deep going on here. It's fairly once you get the argument, it's fairly simple. All right. So I'll take about. When did I start actually, Jack? Do you remember? Supposed to be 75 minutes, but I'll stop by 10:30. Okay, so what I do in this next 5 minutes is that I'll give you an outline of how this difference estimate can be proved. So the idea is to construct a proper net. So this will be true if I take a fixed point u and some finite set of points v. I can use some basic concentration inequality to show that it happens for that particular choice of u and those particular choices of v. So the idea is to actually construct a proper net such that if you get this estimate for a particular choice of a particular set of choices for u, it will give you the same estimate for all choices of u. So what is the net? The net here is the following. So proof of difference estimate. So let us define Ck, d of d, is that norm of z. And so I cannot take all such points, so I'll have to limit the number of points by I equal to 1 minus. So because I'm looking at the L1 ball, I only have d minus 1 degrees of freedom. So what I do is that I look at the L1 ball, so L1 sphere of radius 1 plus epsilon to the k, floor science, I'll not say explicitly. And then the first d minus 1 coordinates, I all want them to be divisible by this quantity, epsilon times 1 minus epsilon to the k minus 1. So the reason you'll see why this particular choice is there, but one thing you can already see is that the size of this net is of the order epsilon to the minus d. So it does not grow too fast. For example, it's not depending on k, which is important because we're going to take a union bound over this ck. So what we're going to do, so observe that so far I have not said anything about why we use this second moment assumption. I said that I'll prove it for the second moment assumption instead of the optimal assumptions of Cox and Dirac. So second moment kind of makes this step a little nicer. So what we're going to do is I'm going to write an estimate, which is essentially the Chebyshev inequality. And there I'm going to use the second moment. So because the second moment exists, the first moment also exists. So let us say M is the first moment. So let me write Ek is So remember what we're trying to do? We're trying to prove the difference estimate for a net, and my net is Ck. So I'm going to take all points in Ck and all points V that are close enough to U, in the sense that V minus U would be of the order of epsilon times 1 plus epsilon to the k. And I want, so now my choice of C will be something like 10 times M times D. So where M is the first moment of the passage time distribution. So I want this to happen for all U in Ck and all V which are close enough to U. Now this, I will bound the probability of the complement of this using a Chebyshev inequality. So let me simply write it down. So probability of Ck complement is less than equal to, so I'm summing over all points in Ck, which is C times epsilon to the minus D. So this is a union bound, and then I sum over all V. So this is, so I needed to sum over all U, and then I needed to sum over all V which is close enough to U. So sum over U is the epsilon to the minus D outside, and the sum over V, because of translation invariance, I have now shifted U to 0. So the sum over V is now simply for all V with norm V with the given upper bound, that probability T0V is sufficiently large. Now this is where I'm going to use their tail information. So remember, so we had already talked about there are 2D many edge disjoint paths connecting any two vertices, and you can see there exist 2D edge disjoint paths with at most so you can also see it's easy to check. You can just draw the figure. So you can choose such 2D many edge disjoint paths such that each of them have at most norm V plus 2D many edges. So let us call this N. So probability that probability that any such path violates the condition. So any such path has length bigger than 10 md times epsilon times 1 plus epsilon to the k is upper bounded by Chebyshev inequality. So I have probability is upper bounded by probability Sn. So Sn is like a simple random walk with increments distributed like f. Is bigger than 10 times. So there are 2D many paths with at most n edges. So the total weight, will be stochastically maximum when I take all of the weights to be, all of the paths to be of length n. So the upper bound of such a path having weight bigger than 10 md times epsilon 1 plus epsilon to the k is simply upper bounded by this, and then I use Chebyshev inequality, so this is exactly where I use that the variables have second moment. So the variance is of the order of n because there are sum of n many random variables, and then Chebyshev gives me this. Now, because of my assumption of on n, so n is roughly norm of v, whereas that 10 times d epsilon 1 plus epsilon times 1 plus epsilon to the k, that is much larger than n. So this quantity is of the order of 1 over n. Right. So what I do is now, so I'm going to sum, or okay, so maybe that is not the useful thing to write. What is useful thing to write is that for all choices of v, this quantity is still of the order of 1 over. So this is true for all choices of n in my range, which is n between 1 and norm v plus 2d. And then also for all choices of v, which is norm v is less than 4d epsilon times 1 plus epsilon to the k. So this is a uniform upper bound for all such things is this. So now I have to sum over all d, right? So I get an epsilon to the so what I get is that I have to sum over all v. So this probability, I'm not being very detailed here, but I just want to give you an idea. You can try to complete the details on your own. So this is less than equal to c epsilon to the minus d. Then I want to bound all, I put an estimate on the number of all possible v, which is like epsilon times 1 plus epsilon to the k whole to the d, and then I get. So this is for a single path. Remember, there are 2D such disjoint paths. So I get whole to the 2D. So I get a kd exponent here and a minus 2kd exponent there. So the final thing will be of the order of c prime divided by 1 plus epsilon to the kd. Now this is summable in k. So Borel-Cantelli lemma tells you that Ek probability, summation probability Ek complement is finite, which means Ek complement cannot occur infinitely often, which means that from some k0 onwards, Ek must happen. So let us assume k equal to k0 to infinity, Ek occurs. Then one can show that TUV is less than equal to some, say, 25 dm epsilon norm u for all u c with norm u bigger than 1 plus epsilon times k0. Okay, so suppose we have shown this, that if Ek occurs from k0 onwards, then the difference estimate holds true for all u bigger than 1 plus epsilon to the k0. Now, because I know that there exists, so on a probability 1 set, there exists a k0 for which Ek occurs from k0 onwards, then for any sample point on that particular set, for all large enough u, this will occur, which is exactly what the difference estimate requires. So, but one more step is remaining, which I will not do, is that you have to go from Ck to all points. No, so I'm only dealing with Ck here, but how do I take care of points between 1 plus epsilon to the k and 1 plus epsilon to the k plus 1? Is simply you look at the closest point. So if your u has norm of u between 1 plus epsilon to the k and 1 plus epsilon to the k plus 1, you simply pick a u0 which is closest in Ck. And then take for any u and v, you approximate tuv by tu0v and tu0u, sum of those two, and then you will get that a similar estimate you will be able to do for all u between 1 plus epsilon to the k and 1 plus epsilon to the k plus 1. So that is the part that I will not write down. I'll leave that to you to work out the details. So yeah, sorry for taking a bit longer than I planned, but this is all I wanted to say. So any questions? Let me see if there are any questions. Okay, so maybe we'll stop for a break and then we'll start at 11.